So in addition to characterizing matter with solid, liquid, gas, we can also characterize matter as a pure substance versus a mixture or a non-pure substance. Now, why do we care? Well, because understanding whether or not a material is pure or not will provide knowledge on how a material's properties will present. All right, so it's useful knowledge when we go to design and build things. We can classify matter in two different main categories: pure substances and mixtures. So the question I want to ask you, and I'm going to make you stop the video in a second and answer this question, is what is your scientific definition of a pure material and a mixture? And I want you to give me an example of each. Now it says here, go to the Jamboard. Don't even do that. Just write it on your piece of paper. This lesson was supposed to be done also in class, which way I would have you go on a Jamboard. But no, you're just going to look in your notes, and you're going to take a piece of paper on the top of your notes, and you're going to write down my definition of pure material is, my definition of mixture is. Here are my examples. All right, so stop the video now and do that. Stop. Okay, so a pure substance, pure material, has the same properties, characteristics, and identical composition throughout the sample. So if I was to take my sample, here's my piece of sample, and I'm going to take a little cut here, a little cut here, a little cut here, 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 and here, and I'm going to change that, and I was going to say the composition from here, 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 and here are comp is all equal. So the composition is all equal throughout the sample, no matter where I take my cut. The other thing is they cannot be separated by physical methods. In other words, I can't take a hammer and cut this in half or whatever and make it something different, right? They can't be separated by physical methods, and there's only two things that are pure materials: elements and compounds. The most basic, fundamental building block of all matter that has unique properties in only one type of atom is an element. There are about 120 of them. This question is always asked to students every year, and many, I wouldn't say many, some struggle with it. I ask, give you a list of materials, and I ask, which of these is an element? And the answer is, whatever one is found exactly as it's listed on the periodic table. So for example, if I list this as a choice, AgCl, that is not an element. The Ag is an element by itself, and the Cl is an element by itself, but they are not an element together. So that's not an element. So that would not be considered an element. So you look on the periodic table. If it's not listed exactly as that on the sheet that I'm giving you, then it's not an element. And here are some examples, and we'll get into what the numbers are later. Copper, selenium, bromine. Those are some of the elements. So a common question I ask sometimes is, describe air. And a lot of students write, air is a element. And air is not an element. Air is a mixture of elements. It's a mixture of nitrogen and oxygen. About 78% of it is nitrogen, about 21% of it is oxygen. So that's about 99% of the composition of air is those two elements. Nitrogen is an element, oxygen is an element, but air itself is not an element. Air is a mixture of elements. Same thing with coal. Coal is predominantly carbon, mostly carbon, or at least 50% of it's carbon. But it's not pure carbon, and therefore it's not a pure material. So again, for something to be a pure element or an element, it has to be listed exactly like it's written down on the periodic table. So I want you to answer these questions in a few seconds. How many of the elements of the 120 known are found in the human body? Now, when I say they're found in the human body, I mean they could be bonded to other elements, but they are found somehow in the human body. And the same thing with your smartphone. How many of the elements are found either in compounds or by themselves in a smartphone? So when you're ready, stop the video and answer the questions. So stop the video now. Okay, so there are about 25 elements in the human body, and the three that make up most of the human body, about 93% of it, are oxygen, carbon, and hydrogen. With oxygen being the most prevalent in your body, almost 2/3 of your body is weight in mass is on the oxygen part. 20%, about roughly 20% is carbon, and then about 10% is hydrogen. So they add these up, this is about 93%. The rest are all these little trace elements here. There's a little bit of nitrogen, some calcium in your bones, and then the rest of this is all 1% or less. All of these elements added together, their weight percent is less than 1%. So again, most of your body is these three elements. Now the answer to the smartphone question is there are about 30 elements. So there's about 30 elements. So 30 elements. Now let's look at a couple of these things here real quick. So about the 30 elements, right? Here's oxygen. It's found in the battery, the screen, and the electronics. There's some copper, there's some aluminum, gold, some silver. Now, let's look at some of the ones that are less common that you might not know of. Neodymium, that's used for magnets. Gadolinium, thorium, terbium, dysprosium, europium. I mean, those are very esoteric, uncommon elements, but they are used in your cell phone. So about 1/4 of the elements that we know of are found in your cell phone at some level. And this is a quick slide on the elements found in fireworks. I just wanted to show you something here. If you're making, red fireworks, you use strontium compounds, and if you want to make blue fireworks, you make copper compounds. But again, what's red and plus blue? Well, that's going to be violet. So if you want a violet compound, you mix strontium and copper together. You know, it's simple. When you mix your two red and blue crayons to make purple, that's what you're doing. Here's some of the other ones that are listed, right? So anytime you go to the fireworks now, you can say, hey, look, those are different colored compounds that are making those fireworks look different. There are 7 elements that are called the diatomic elements. Di means 2, and then atomic means atom. So these elements have 2 atoms bonded together in the free state. What I mean by the free state is I say elemental oxygen. That means that it's just oxygen by itself, and that would be O2. So you can see the 2 here means that there are 2 atoms of oxygen, 2 atoms of hydrogen, 2 atoms of chlorine. In water, there's only 1 atom of oxygen, and therefore it's not in the free state. Free state means it's by itself. And here are the 7 right here. Now you're going to have to memorize this list, but I'm going to teach you a little trick on the next page of how to do that. Okay, so here's the trick, and it all involves the number 7. So 7, 7, 7. Keep thinking that. There are 7 diatomic elements. I'm going to start at 7. I'm going to make it 7, all that stuff. Okay? So the first thing we're going to do is start at 7. So where is my 7? There it is. See, there's the 7. Nitrogen is the 7th element. Count them. Right? 1, 2, 3, 4, 5, 6, 7. Okay. Now we're going to make a 7. So when we make a 7, we're going to start and move this way, just like a regular 7. Now, we have to make a decision. Do we stop at O, F, or NE? Well, we're going to stop at the F, because the F is pointing down. So we follow the F down until we get to I. Right? I is the end point. All right, so let's count how many we have so far, because that's in key. So there's 1, 2, 3, 4, 5, 6. Where's the 7th? Here's the last part of the rule. Start at 7, make a 7, add 1. And where's my 1? Right here. So at the end of the day, that's 1, 2, 3, 4, 5, 6, 7. So there they are. So a compound is just a mixture of 2 or more elements chemically combined in fixed ratios. What I mean by that, a fixed ratio is CO2, carbon dioxide, is always going to be CO2. It's never going to be CO3. It's never going to be CO 1.5. It's always CO2. So it always will have 1 carbon atom to 2 oxygen atoms. Carbon monoxide will always have 1 carbon atom to 1 oxygen atoms. The ratio is fixed for that particular compound. The properties of the compounds will differ then from those of the elements that make it up. Hydrogen is a very flammable gas. Oxygen is necessary to keep a fire going. So you need, when they say they need fuel, oxygen, and spark. So if you mix oxygen and hydrogen and add a spark, you get an explosion. If you chemically combine them, you get water, and water is used to put out a fire. Compounds can only be broken down into the simpler substances by a chemical change. C is compound, C is chemical. Okay? So if you wanted to break water down into its components, you could do that by electrolysis. So water would then become hydrogen and oxygen, 2 diatomic elements. When we mix 2 or more substances, remember what a substance is. That is a pure material. So we mix them 2 together, 2 or more of these together, and we don't chemically combine them, we get a mixture. So for example, table salt and water. So if I add salt to water, there's no chemical change going on there. It's just mixing salt and water. And how do I know that? Because if I evaporate the water, I get the salt back. Air is a mixture of nitrogen gas, oxygen gas, and a little bit of CO2 and some other stuff. Soil is a mixture of water, dirt, sand, rock, whatever, earthworm parts. Okay, they're all mixtures, right? They are not chemically combined. So the characteristics of mixtures are that they do not have a fixed ratio between the substances that make them up. So a prime example of this is if you're making a drink mix, let's say you want to have a lemonade, right? And you're doing one of those scoops of lemonade crystals into water. If you find it's too sweet, what do? You add a little bit more water, right? You're not confined by the ratio. If you find it's a little too weak and you want to add a little bit more sugar mix, then you do that with the mix, right? So there's no fixed ratio. The properties of each of the substances that make up the mixture remain unchanged, and then they can be mixtures can be separated by physical means. That's a key word here, physical, right? And what do I mean by that? I mean things like filtering, sorting. Sorting would be like if you have a big pocket full of change, pennies, dimes, nickels. You would put the change here, and then you would say, okay, these are all the pennies. Here's a penny, there's a nickel, there's a dime, another penny, another dime, another nickel. You would physically sort them using your hand, right? Decanting is what they use generally in a sewage treatment plant when, we'll just call it waste, right? Lack of a better word, or, you could call it poopy water. When that comes into the sewage treatment plant, what they do is they let that stuff settle first to the bottom, and then they pour off the water on the top, or they separate the water on the top, and then that's further treated before it goes out into the harbor or back into the system or whatever, right? And then that solid stuff gets further processed down the line. Centrifuge is how they separate blood into plasma, white blood cells, red blood cells. Chromatography, we're going to do a little lab on that. That's the separation of things by relative speed through a media. Distillation is how they separate two liquids, generally that have different boiling points. Okay, so we've talked about the different types of pure substances. Are there different types of mixtures? So I want you to, when I tell you to stop the video and answer the question. Are there different types of mixtures? And if there are, what are they? So think about that. Stop the video now. The first type of mixture is a homogeneous mixture, and homo means the same. And then the components are uniformly dispersed. In other words, no matter where I take my little piece of that sample, the composition is going to be the same no matter where else I take a sample. So let's make a little drawing here. Here's my little box of stuff, and let's say this is the thing, and I'm going to take this piece of the block and this piece of the block, and I'm going to call this C1, composition 1, and this is composition 2. So the composition of 1 and 2 is exactly the same. No matter where I take my sample, it's going to be exactly the same. And so best example of this would be dissolving salt in water. When I fully dissolve salt in water, the salt goes everywhere, right? There's no separation of the salt in the water, right? Air would be another example. Brass, copper and zinc, and stainless steel, which is iron, a little bit of chromium, a little bit of carbon. Homogeneous mixtures are solutions. People always think that solution means liquid. It's not true. A solution, for our definition, is just a homogeneous mixture. Solid solutions, metallic specifically, are called alloys. So, for example, anybody who owns any type of jewelry probably has some type of alloy for their main metal. So if you have gold jewelry, there's probably a little bit of silver or platinum or maybe even copper in there. It's not pure gold. Sterling silver, same thing. There's mostly silver, but there's some other stuff. If you have pure silver, generally it'll tarnish pretty easily because it turns like the grayish, greenish mess, right? White platinum, white gold, things like that, right? Stainless steel is a alloy, as is brass. The other side of homogeneous is heterogeneous. Hetero means different. So the different composition throughout. So if I made my box and I took my C1 here and then my C2 here, C1 does not equal C2. So the composition will vary depending on where I take my sample. So examples here would be pile of salt and pepper, garden salad, you have big hunks of tomatoes and maybe croutons and like lettuce and stuff like that. Concrete, sand and water, chocolate chip cookie. So another example, an easy example to show the students is this. Let's just make a cookie here. So here's my cookie. And then we're going to add some chocolate chips to it. There's a chip, and here's a chip. Here's a chip here, and maybe this is a chip here. So if I took my sample right here, we'll call that C1, composition 1, and I took my sample right here, composition 2, you can see that there's going to be a different composition on that. So again, chocolate chip cookie is a great example of a heterogeneous mixture. Okay, so we're on the last two slides of the lesson, and this is what I want you to do. When I tell you to stop the video and copy these words down, right here, copy these down onto your notes or a scrap piece of paper or whatever, and then you're going to list whether or not it's an element and putting the letter E, compound, put the C, homogeneous HO, or heterogeneous HT. So what you're going to do is you put them down, right, and then you're going to check your work on the next page. So stop the video now. Okay, so here are the answers. Now I'm only going to focus on one answer because you can read the rest of it. Let's look at this water with ice, right? And this is a kind of a curveball for many students when they first see it, right? And let's try to understand why the answer is compound and not mixture. And then so let's look at the definition of a mixture. A mixture is two or more different things physically combined, right? So you could say, well, look, if I'm looking at a mixture, the water is different than the ice, right? So one's a solid and one's a liquid, and if I take a little sample of the liquid, I could get a big chunk of ice and a little bit of water. If I take another sample, I could get a big chunk of water and a little bit of ice, and that might be the case, right? And that's true, right? But that's not the definition of mixture. A mixture is two or more different substances, and ice and water are the same substance. They are both H2O. One's solid H2O and the other's liquid H2O, but it's both H2O. So the chemical composition between the two has not changed or is not different. What is different is the state of matter, and in no way has the definition of our mixture anything about state of matter. It says two different substances, and ice and water are the same exact compound. Okay, so if you did well here, or maybe you got the last one wrong, that's okay. If you got most of the other ones right, when I say most, I'm saying if you got maybe two wrong and you understand why you got them wrong, that's good. If you got more than three wrong, I think you need to go back and review a little bit about what each one of these are. If you only stumbled on the last one, I think you're pretty good, right? Yeah, I don't think you make that mistake again, all right? If you really struggled with this, you can either go back and review, or find a friend to help you, or you can just send me an email and we will work it out somehow, either through a quick video chat, or I can probably give you some helpful hint just through email, all right? So that's the end of the lesson.